Okay, so basically, due to the fire alarm, we were left to we have a few more things we needed to discuss. So basically, we talked about the Venn diagrams of schedules. We have all schedules, and often we're given a concurrent schedule. We need to check whether it is serializable, and conflict serializable and view serializable schedules. So basically, these are the conservative tests. So if something is conflict serializable, it is definitely view serializable. And however, if something is view serializable, we cannot say the reverse is true. So in the remainder of today's lecture, we're going to briefly talk about conflict serializability and how to check whether something is conflict serializable. And on Thursday, we're going to talk more about view serializability. And then after that, we're going to talk about multi-version concurrency control. So today, in the remainder of the lecture, we're going to talk about conflict serializability. So basically, conflict serializability is based on the notion of conflicting operations. So um, we need to consider a pair of transactions. If two transactions are operating on the same data item, and one of the operation is a write, then they are in conflict with each other. So basically, let's say that we have T1 and T2. So R1X means that transaction 1 is reading X. R2X means that transaction 2 is reading X. And then here, our W1X means that transaction 1 is writing on data item X. And W2X means that transaction 2 is writing on data item X. So we only have two operations are conflicting operations, even only if they are operating on the same data item, they are from different transactions, and also one of the operation is a write. So basically, if two transactions are both reading the same thing, then there is no conflict. But if I'm reading something and then you're writing on it, or if I'm writing on it, you're reading on something I've written, then we have a conflict. So two transactions are conflicting, potentially conflicting each other, then if and only if they're from different transactions, they at least one of them is a write operation, and also they're operating on the same um, data item. So the motivation is that when two transactions have a conflict, then it is very possible that flipping the order of this operation will change the end result. So the motivation behind conflict serializability is that we are allowed to swap the order of non-conflicting operations, and for the conflicting operations, we need to keep them the way they are. And if we can swap the order of non-conflicting operations and transform that into a serial schedule, then we're saying that the schedule is conflict serializable. So here, this is the process of transforming a concurrent schedule to a serial schedule by only flipping on the non-conflicting operations. So if after a series of swapping of non-conflicting operations, we get a serial schedule like that, then we can say that the original schedule is conflict serializable. It is conflict equivalent to a serial schedule, and thus the original schedule um, is conflict serializable. And based on our previous exposure to the Venn diagram, we know that if it is conflict serializable, it is definitely serializable. So this is the strictest test. And a lot of times we don't want to play the game of swapping these operations because it will be super slow. And what we end up doing is that we build a precedence graph and then see whether there is a cycle in the precedence graph. if there is a cycle in the precedence graph, it means that there is a circular dependency of the transactions, and then we cannot really swap the non-conflicting operations into a serial schedule. So this is the actual test for conflict serializability. What we do is that we look at each pair of operations and check whether it is conflicting. If they're conflicting, then we need to draw an arc from the previous transaction to the later transaction, and in the end we make a graph like that, and we need to check whether there's a cycle in it. So in here, so basically, let's say we have a schedule like this, and then for we need to pick one operation first, and then see what are the conflicting operations compared to Rx performed by transaction 1. For transaction 1, because it is already a read on X, so the only thing that can be conflicting with it is that maybe some other transaction is writing on it, and the only ones that are writing on X are T2 in here and T3 in here. So basically, Rx and Wx from T1 and T2, these two operations, they're conflicting. So we draw an arc from T1 to T2. So there's an arc from T1 to T2. And then because Rx precedes Wx in T3, we also draw an edge from T1 to T3. So that's another edge over there. And then we go through all possible pairs of operations across transactions. And if they're conflicting, we draw an edge like that. In the end, we're left with a precedence graph. And we can see that it definitely has a cycle. So T1 goes to T2, T2 goes to T3, T3 goes to T1. So there is a cycle in this precedence graph, which means that there is no way for us to rearrange the non-conflicting data items and transform that schedule into a serial schedule, which means that this schedule is not conflict serializable because we have a cycle in the precedence graph. And we can go through more examples. So so here, this is an easier part because we only have two transactions. So if you have two transactions, we'll have like two nodes. So we need to check whether there's an edge from T1 to T2. So definitely, because T1 has write on X and T2 also has write on X. So there is an edge between node 1 to node 2. And if you look at Rx in T2, it precedes the are there any data items that are conflicting with it? Well, you're reading X, so T1 is reading Y. They're not conflicting because they're operating on different data items. And T1 is writing on Y, and T2 is reading on X. So this is still not conflicting because they're operating on different data items. And for the last operation in transaction 2, so transaction 2 is writing on X, and after that T1 is writing on Y. So there is no edge from T2 to T1 in the precedence graph. So in that case, the first schedule is indeed conflict serializable. And you can apply the same logic to the second example and check where there is an edge from T1 to T2 and check whether there's an T2 to T1. So so basically, I've spotted two write operations. So in T1 we're writing on X, in T2 we're also writing on X, and T1 write precedes T2 writes. So there is definitely an edge from T1 to T2. And what about if there is an edge from T2 to T1? In order for us to have an edge from T2 to T1, we need to have an example where we have two conflicting operations, and the first one is in T2 and the second one is in T1. So if you look at the read operation in T2, it is in conflict with the write operation X in T1 because one of them is writing, and then they're operating on the same data item, and also they're from different transactions. So Rx in T2 precedes Wx in T1, and this is a conflicting operation, and we need to add an edge from T2 to T1. So there's an edge from T1 to T2, and then an edge from T2 to T1, which means that there's a cycle, which means that the second schedule is not conflict serializable. And we'll talk more about view serializability on Thursday.